Hello everyone, I am Dr. Osman reporting from the University of KwaZulu-Natal, the premier University of African Scholarship. Today we begin a series of video lectures on material and energy balancing, which is taught typically at the first and second year levels of any chemical engineering degree. You will learn how to use the principles of conservation of mass and energy in order to solve material and energy balancing problems in industry, as well as work out the energy requirements for any particular process. We will begin firstly by looking at material balancing and thereafter expand our understanding to energy balancing. Many of the examples in the series of videos are from the book Introduction to Material and Energy Balances by Reklaitis. It is a very comprehensive book. I highly recommend that you either order it online or purchase it at any university bookstore. We will go through some of the examples in this book. However, it has many more examples, so if you want a more thorough understanding, you really need to get this book. I hope that these videos will be of great use to you and you will be able to watch it over and over again if you require a more thorough understanding. So please feel free to comment below as well as provide any constructive suggestions on how to improve these videos. Okay, we will begin firstly by looking at material balancing, and we will just have a short introduction and as well as an introduction to the notation and the concept of independent and dependent variables. So let's get straight to it. Okay, firstly, why do we as chemical engineers need to have a good understanding of mass balancing? The first reason is obvious, of course, right? In a chemical process industry, we have many units. They could be separation units or they could be reacting units, right? Reactors or separators. And whether these are reactors or separation units, we will be feeding these units, right? These are ultimately things like distillation columns or stirred tank reactors or plug flow reactors, and ultimately we are feeding them with inputs and we want to know what the output will be. Okay, so that's quite an obvious reason. We may have multiple inlets and outlets, such as in this example, and so we need to know what the outputs will be given a certain input. The second reason is that a good understanding of mass balances can save us lots of money potentially. Okay, for each stream, we would like to know what the flow rate and composition of each component is in each stream. Now, an amateur's approach would be to simply install a flow meter in every single stream. And remember, these physically resemble pipes. So installing a flow meter in every single pipe will be very expensive. And not only that, an amateur's approach would also require us to have many sampling points and continuously take samples and measure them for the composition of various components in our streams. Now, adding in so many flow meters is costly, and also for composition, it's not typically done on a real-time basis. We often have to draw lots of samples to get composition of each stream. So we would like to minimize the amount of flow meters and also composition measurement that will be necessary. Okay, so an engineer's solution will be to take as little amount of measurements as necessary and calculate the flow and compositions using rigorous and scientifically sound equations and computations. Flow meters can cost up to $1,200 or even $1,500 US dollars or more. Composition measurement is even more expensive. And the reason why a competent engineer is, of course, so highly paid is because his actions and decisions ultimately save the company even more, right? Whichever company he's working for, or even if he's working on his own, by himself. Okay, so our knowledge can save a lot of money. Now, this particular example is an example of a life support system which is typically used in medical applications. However, it can be scaled up to produce methane on an industrial scale, but that's typically not ideal, so it's typically used in small processes, on a small scale. So and it of course has many different units. We can see mixers here, also a separator, a condenser and separator, and 3 reactors. Okay, so it's a fairly complex example for us to tackle at this stage. So we will first look at a much simpler example just to grasp the notation and the approach to mass balance problems, and thereafter we will build upon that knowledge. Okay, so let's consider a basic problem. Okay, so let's look at a simple problem. This is a separator. It could be any kind of separator. It could be a membrane separator, it could be a distillation column, or a simple evaporator. And we have one input containing 3 components. I'm just calling them A, B, and C. These could represent compounds, okay, chemical compounds, but for now we're just taking an arbitrary example. So components A, B, and C. And the aim of any separator would be to try and separate our stream and purify each component. As you can see, this particular separator doesn't really do a very good job of separating the components A, B, and C. However, it does accomplish one task. It at least separates into 2 streams where we have A and B primarily at the top with no component C in stream 2, whereas stream 3 still has perhaps a small measure of A and B, and of course all of the C. Ideally, well, realistically, separation is not perfect, it's not ideal, so we have many separation units. Both of these streams will go on to other separation units for further purification. Okay, now I'm using this simple example just to illustrate or to get you well acquainted with the notation. So let's first focus on a single stream. Okay, and I think I'll just draw it here. Okay, so that's stream 1. I hope it's clear enough. Okay, and it contains components A, B, and C. Now the molar flow rate, or the total molar flow rate of the stream, we can state to be N1. Okay, so that's the total molar flow rate of stream 1. Note that I have components A, B, and C. I can number them 1, 2, and 3. Now if I want to look at or perform calculations on the flow rate of just component A in stream 1, then we can talk about a notation of N1, A. Okay, and this denotes the flow rate of component A in stream 1. I could also, since I am numbering it, I could also write it in this fashion, N11. Okay, so that is our notation for our flow. If I have to look at, for example, stream 2, okay, that's stream 2 with A and B. Then N12 N21 would denote the flow rate of component A or component 1 in stream 2. If I have to look at the flow rate of component B in stream 1, that will be written as N1B or N12. Okay, now in general, we can write that for any particular stream, for any component in any stream, we can say that Ni, J is the flow rate of component J in stream I. Okay, so it's very important you have to get the notation correctly. And an alternative way to express this is, I know many textbooks, they write it in this fashion. In J, and they put the I at the top. So whatever is at the top denotes the stream number and the J denotes the component number. So for example, instead of writing N12 like I've done here, I can also write it in this fashion. Okay, and that denotes the flow rate of component 2 in stream 1. Okay, and remember that we are talking in molar terms. So these are all molar flow rates. These could be kilomoles per hour or mole per second. The fact is, it will be a molar flow rate. Now, if we are writing in mass terms, then instead of writing N, we use F, okay, to denote a mass flow rate, and this will be in kgs per hour, or simply just grams per hour, or kg per minute, any quantity of mass per unit time. Okay, so that's it for the flow. And also in mass terms, we can write or express things in the same fashion. The flow rate of component 2 in stream 1 is F12, or we could write it in this fashion. That doesn't change. Okay, it's just that we have F denoting a mass flow rate and N denoting a molar flow rate. If we have to look at composition, okay, for any particular stream, let's look at stream 2 containing A and B, which I have numbered. Then Xij denotes the mole fraction of component J in stream I. Okay, so for example, X21 is the mole fraction of component 1 in stream 2. If I have to look at stream 1, then X13, for example, will be the mole fraction of component 3 or component C in stream 1. Okay, I can also write this in this fashion here. Okay, I don't have to number the components. I could write the components out as well. Okay, and also we can use same like with the flow rates, with the composition. Instead of writing X13 in this fashion, we can write X13 in this fashion. Okay, and many textbooks have used this type of notation. And remember that X will always denote molar flow rate, molar composition. Okay, for mass composition, we can use W. where Wij is the mass fraction of component J in stream I. Okay, so for example, W32, for example, will be the mass fraction of component 2 in stream 3. Now, in a mass balance problem, we work either in molar terms or in mass terms. So you will either find yourself working in terms of N and X, right, your molar flow rate and molar composition, or your mass flow rate with mass composition. It's very important that you do not confuse these two. Okay, you cannot use a mass fraction with a molar flow rate. You cannot use a mass flow rate with a mole fraction. So if you are confronted with any problem and they are giving you the information partially in molar terms and partially in mass terms, then you immediately, it should be instinctive that you will need to convert either all of the information given in mass terms to molar terms, or convert the information given in molar terms to mass terms. Okay, we can also write also remember that we can express our molar flow rate of any component in terms of the total flow rate. Okay, so for example, the molar flow rate of component 2 in stream 1 is equal to the mole fraction of component 2 in stream 1 multiplied by the total molar flow rate, N1. Okay, or in mass terms, the mass flow rate of component 2 in stream 1 is equal to the mass fraction of component 2 in stream 1 times the total mass flow rate of stream 1. Okay, so for any stream I, okay, so for any stream I, we can write Ni is equal to the sum of j is equal to, j is equal to 1 to n of Ni j. Okay, or we can write the same in mass terms. Okay, the summation of all j components in that particular stream. Okay, and at this point I need to reiterate once again, we can only use molar flow rates with mole fractions and mass flow rates with mass fractions. Do not confuse these two. Now, if we are given information partially in molar terms and in mass terms, we can go between mass balancing and molar balancing by using simple conversions using the molar masses of our compounds. Okay, so N12, or the molar flow rate of component 2 in stream 1, is equal to the mass flow rate of component 2 in stream 1 divided by the molar mass of component 2. Okay, so M is your molar mass, and that could be in grams per mole or kilograms per kilomole. It just depends as a matter of convenience. Okay, we can also express this in many different ways. This should actually just be a revision for you, since this is a second year course. And you would have learned this before in Chemical Engineering Principles 1 if you are at the University of KwaZulu-Natal. So N12 is equal to X12 times N1, and that is equal to F12 over M2, or we can re-express F12 in terms of the mass fraction over M2. For any particular stream, and I'm just using stream 1 as an example. Remember, this applies to stream 2 and stream 3 as well. Okay, note that your total flow rate of stream 1 is the sum of the flow rates of all the components. Okay, and we can write that in terms of our mass flows as well. Okay, or we can express it. We can express our molar flow rate, our total molar flow rate of stream 1 in terms of the total mass flow rate of stream 1 over this m bar, where m bar is a mole weighted average of your molar masses of all of the components. Okay, so we're looking at a mole fraction. Remember that our m bar is a function of our mole fraction times our individual molar masses. Okay, do not confuse this with mass fractions. In this case, we have to use a mole fraction. Okay, so in the case of stream 1, for example, this can open up okay. Another convenience that we can write is our mole fraction of component J in stream I. We can express it in terms of our flow rates, our molar flow rate of component J in stream I over the total molar flow rate of stream I. And we can express this in mass terms as well, using our molar masses. Okay, so that's our mass flow rate, component J in stream I, over our molar mass of our specific component J, all over the summation of our molar flows of each component, which is of course equal to our Ni. Okay, and this is summing up J components. And ultimately we can write this in the following fashion. Okay, that's your total flow rate, your total mass flow rate of stream I times the mass fraction of component J in stream I divided by the molar mass of component J, and we can express our molar flow rate in terms of mass flow rates as well. Okay, that's Wij over Mj. So we are summing up all of our components in this denominator here, and this is the mass flow rate of the component in question. Okay, so remember that this is ultimately what we want to obtain. Okay, and we can also express this simply as Wij over Mj, well, that's your molar mass, over the following summation. Okay, and these are the different relationships between our mole fraction and our mass fraction. We can also express our mass fraction finally in terms of an average molar mass, where our m bar is expressed as follows. So let's just see if I can fit it here. Okay, so your mass fraction of component J in stream I is equal to Xij times Mj, all divided by m bar, where this is your m bar is your mole weighted average of your molecular masses or molar masses. Okay, now I've gotten from this relationship to this relationship using the relationship that my mass flow rate is equal to my molar flow rate times the mole weighted average. Okay, that is everything there. Okay, so now that you have gotten a good grasp of the notation of how we express mass fractions, mole fractions, mass flow rates and molar flow rates for each stream in any particular problem, we can move on and discuss another issue, and this is the issue of independent variables. Okay, so let's get on with it. Okay, independence is an important part of solving mass balance problems as well as energy balance problems. So let's look at a simple example. Let's look at the feed stream of the separator that we've just worked with. Okay, so let's look, it was numbered as stream 1 and it had 3 components, A, B and C. Now we need to ask ourselves, what do we need to know about the stream in mass or in material balance terms? Ideally, we would want to know the flow rate of each component in the stream. If we know the flow rate of each component in the stream, we can get the total flow rate. And if we know all of the flow rates, then we can obtain all of the compositions. If we are given a mass flow rate, we can obtain the mass compositions quite easily. If we are given molar flow rates, we can determine molar composition quite easily. And if we know the molar masses of each of these components, then we can convert between mass and molar terms. So let's add some values to this example. Let's consider a case where we are told that the total flow rate of stream 1 is perhaps 100 kilomoles per hour. Okay, and we are told that the composition for component A, okay, I'm just going to call this X1A. Remember, I can also refer to it as X11 if I'm attaching a number to each component. Let's say, for example, that it's equal to 0.1. And let's say, for example, that for component B, we have the composition given as 0.4. Now recall that our compositions must of course add up to 1. Now let's say, for example, they've given you the composition of part C, of component C, to be 0.5. Okay, so this is essentially all of the information that we need, really. I mean, we have the total flow rate and we have all of the compositions, so we can get all the information that we require in molar terms for our material balancing. Now, one thing worthy of note is that we have a total flow rate and we have 3 compositions. However, we know that our compositions must add up to 1. So it was quite unnecessary for them to tell us that the composition of C is 0.5. We could very easily just determine this. Right? We could say that X1C which is of course X13 if I'm numbering them, that is equal to 1 minus 0.1 minus 0.4. Okay, so it was quite unnecessary for them to give us this composition because it was very easily calculated. It's calculatable. Let's consider another scenario for stream 1. Okay, in this scenario we have A, B and C, and let's say they told us that the composition of A is 10 kilomoles per hour. And the flow rate is 10 kilomoles per hour and the composition is 0.1. And let's say if they told us that the composition of component B is 0.4 and the composition of C is 0.5. Okay, now we have the flow rate of component A and we have the composition. So we know that 10% of this stream is 10 kilomoles per hour. So we can get the total flow rate. That will simply be 10 divided by 0.1 and we will get our total flow rate. And we are given our composition of B, so the composition of C is still unnecessary. Okay, so what seems to be the case is that as long as we have one flow rate and 2 compositions, we seem to be able to get everything we need. Now let's look at another scenario. Okay, let's say if they have given us A, B, and C, the compositions are once again 0.1, 0.4, and 0.5. Now they have given us 3 bits of information, which is similar to our previous scenarios. I mean, 3 bits of information, just a flow rate and 2 compositions here, and a flow rate and 2 compositions here have provided us with all of the information that is necessary. We could easily calculate everything we need. But in the case of this third scenario here, we are given 3 pieces of information, 3 compositions, one of which is still unnecessary, but note that we do not have any flow. We are not given the total flow, and we are not given the flow rate of any of these individual components. So it seems that in this scenario, we cannot obtain all of the information we want about the stream. Okay, so what we can conclude is that for us to know all the information about a stream, we would always need at least 1 flow value and 2 composition values in the case of this particular stream. Okay, so we will always need 1 flow and 2 compositions. And the amount of information necessary is known as independent variables. Okay, so 1 flow and 2 compositions. So we have 3 independent variables. Anything else that is not independent is dependent. For example, the x1c is a dependent variable because we use the independent variables to calculate it. So a dependent variable is dependent on a calculation of independent variables. Okay, so in this particular stream we need at least 1 flow and 2 compositions. Note that in general for any stream, any kind of stream that you can think of, okay, for any stream with any number of components, let's say for example S components. Okay, I'm using this fancy S here. We can note that we will always need, or we will always require, S minus 1 plus 1 independent variables. Okay, and let's look at this S minus 1 plus 1. So this refers to the number of components or number of compositions that we need. So if we have S number of components, let's say for example 6 components, we will need 5 compositions and 1 flow. Okay, so this plus 1 is a flow. If we had 7 components in our stream, in any particular stream, we will need 7 minus 1 or 6 compositions and still 1 flow. Okay, so that summarizes independent variables as far as streams are concerned. Now let's get back to our separator. Okay, with our one stream coming in and two streams coming out. Now if we had to count our independent variables, we would note that we should be having one flow there and at least two compositions. For stream 3 we would have one flow and also two compositions. The third one we can get by difference. And for stream 2 we would need one flow and one composition. The other we can get by difference. So if we had to count the number of independent variables for the separator, we could count as follows: one flow and two compositions, that's 3. Another flow and two compositions, so that will make 6. And one flow and one composition, so that makes 8 in total. Okay, so 8 independent variables for the system. And ultimately this means that if we have these 8 independent variables, then by calculation we can obtain all other variables, all dependent variables. Now let's get to the main stuff. Let's look at performing an actual mass balance or material balance over the separator. And we can talk in terms of moles. Remember that this is simply a separator, so whatever material is going in will ultimately be equal to the amount of material coming out. In other words, the summation of these two streams will add up to the input stream. So let's look at the number of balances that we can write. Firstly, we can write a total balance. Okay, and that would be the total flow rate in stream 1 should be equal to the total flow rate in stream 2 plus the total flow rate in stream 3. So that's one balance equation. We can also write component balances. Okay, and so in terms of component 1, 2, and 3, the flow rate of component 1 in stream 1 is equal to the flow rate of component 1 in stream 2 plus the flow rate of component 1 in stream 3. And we can continue our component balances for the other components. That's for component 2, and finally for component 3. We can also write these balances in terms of our mole fractions and total flows. Okay, so this is just a re-expression of these 3 component balances here. Okay, N11 is ultimately equal to X11 times N1. Sorry, that is X21. So X31 times N3. Okay, and for component 3, okay, and so these three balances are equivalent to these three balances here. Okay, so this is just an alternate expression of these three balances, these three component balances. Now, another issue arises. Do we really need all four of these balances? Okay, and that is a valid question to ask. I mean, can we perform the computation with using perhaps just three balances? And this is where independence comes in as well, because not only do we have independent variables, but our balances are also we can also have an independent set of balances. Okay, not every balance equation is necessary in order to perform the computation and get all of our flow rates and all of our compositions. Okay, and this is for the simple reason that I can re-express these terms as a function of the other terms. For example, let's look at the fourth balance equation here. N13 is equal to the total flow rate in stream 1 minus the flow rate of component 1 minus the flow rate of component 2. So I can re-express this balance in terms of the other three balances. So if we solve equations 1, 2, and 3, we can obtain equation 4 by difference. And this is true whether we are expressing the component balances in terms of our molar flow rates or in terms of our compositions, our mole fractions. Okay, and that is because x13 is equal to 1 minus x11 minus x12. So we find that not only are our variables dependent or independent, but our balances, our balance equations can also be dependent or independent. For this particular case, we have a maximum of 3 components, and ultimately there are a minimum of 3 independent balance equations. In general, for any separation unit, we can simply count the maximum number of components related to this unit, and that will be the minimum number of independent balance equations. Okay, another thing to note is we have now gotten the notation out of the way. This is, of course, how to write a balance equation. Okay, we can say in is equal to out, or you can even express it in terms of out is equal to in. That's fine, but the main issue is that you have to be consistent and be very neat when writing out your balances. In the past, I've seen students that write out their balances in a rather haphazard fashion, and while they may sometimes understand what is going on and they are simply being haphazard, if they make a mistake, it's very difficult for them to correct that mistake or even realize their mistake. So I cannot stress this enough. You have to write out your balances in a neat and coherent and consistent manner if you want to be accurate about your calculations. Okay, so from this example, we've noted that there are 8 independent variables, and three independent balances. And the reason why we are talking about independent variables and independent balance equations is because we would like to know the minimum amount of information required in order to calculate everything else. In other words, every flow of each component in every stream. And this preliminary analysis is known as degree of freedom analysis. Okay, and we'll look at this in greater detail with an example.